A cylindrical can open at the top is to hold 400 cubic centimeters of liquid. Find the height and radius that minimizes the amount of material needed to manufacture this can. So the can has a height, which I'll call h. It also has a radius, r. And they want us to find the minimum material needed. So that's the minimum surface area of the can. They want the can to be open at the top, which means that the only surfaces we're going to deal with here will be the bottom of it and also the side of it. Okay, so an interesting thing about the side of this cylinder is it could be cut and like unwrapped. By unwrapped, I mean it winds around the can, but imagine letting it totally come apart like this. And now that is like the side of the can. That side of the can would have a height that's still h, but his distance, his length along his edge here, we could calculate what that is. It's going to be his circumference, and we know that the circumference of a circle has a formula of 2 pi r, so that is going to be the length of this shape. If we were to further flatten it out, it would become a known shape. What shape does it become? Yeah, it becomes a rectangle. So that means that this rectangle has a height h and a width there of 2 pi r. So the area of the rectangle then is 2 pi r h. We also know the area of the base. That's just area of a circle, pi r squared. Together they make a total surface area of adding the area of the base plus the area of the side. So that's going to be pi r squared plus 2 pi r h. This is the thing that they want us to minimize. Minimize the material needed to manufacture the can. That's this. As we can see, though, it is a function of two variables right now. And if you're not in multivariable calculus, if you're in single variable calculus, then you want to get that objective function. This is the objective function. Get it down into being a function of one variable. Now, why is it the objective function? Because we're asked to minimize this quantity. Okay, so we have to work with another equation that'll help us simplify it. They also tell us that our cylinder needs to hold a volume of 400 cubic centimeters of liquid. That right there is a constraint equation that they're describing. So we should write that down as well. We need the volume to be 400. Okay, however, we could find the volume of the can based on the variables that we looked at so far. Volume of a cylinder is always going to be the base times the height. So pi r squared times the height. So we need for pi r squared h to be 400 is what they're saying. All right, now we can divide in order to solve for one of these variables. I think I'll just solve for h here. So I'm going to divide both sides of the equation by the pi r squared. And that'll reveal then that h is 400 over pi r squared. It's something that I could now plug in to my objective function. because I want to get that h out of there and replace it with something in terms of r, and now the whole function's going to be in terms of r, so that's great. All right, I'll just call this a for area. It's going to be a function of r now. Okay, so some things should cancel here. The pi's will cancel, one of the r's will cancel. We get that for our simplified objective function. All right, our next step is going to be to differentiate the objective function. So we'll get a prime of r is going to be 2 pi r. This one is going to be a negative 800 over r squared. That'll be his derivative. Now we want to set the derivative equal to 0. And we'll solve for r. Okay, so now we just cancel these off. We're going to get that r is going to be the cubed root of 800 over 2 pi. On calculator, that's about 5.03. Okay, so now I'm going to plug that back into the height formula. And you get that the height and the radius actually need to be the same. So final answer, radius is 5.031 centimeters approximately, and the height is approximately the same.